Welcome everyone, and thank you for joining us for this webinar on experimental modal analysis with ARTeMIS Modal. Before we get started, I'd like to go over a few practical points. First of all, please ensure that your cameras are all turned off and that your microphones are muted throughout the entire webinar, as background noise can interfere with the session, which we would very much like to avoid. And second of all, for questions, if you have any questions, feel free to use this chat function at the bottom right corner, because then Palle will address your questions at the end of the presentation. And also, if you have any questions related to licensing or pricing, you're very welcome to write those in the chat as well, and I will make sure to respond to those as they come in. And with that, I think I am going to hand things over to Dr. Palle Andersen. So enjoy the session.
Thank you very much. So let's see, let me just make sure I have everything under control here. Good. Well, thank you very much, Dieter. Yes, I would like to also welcome all of you to this session here, and I hope that you can see my monitor now. Let me just ensure that this is actually happening. Yes. Okay. So this is a webinar on experimental modal analysis using ARTeMIS Modal. And throughout the next hour or so, I'm planning to go through these different items here. First of all, I'd like to give an introduction to experimental modal analysis in general. And then I'd like to talk about ARTeMIS Modal, of course, and introduce the different plugins we have that are needed in order to make the experimental modal analysis. Then there are different ways we can actually, you could say, start up an experimental modal analysis. No matter how we want to do it, we need something called frequency response functions. And I'd like to show you how you can actually get these, obtain these in different manners and get them into the software. And then finally, I'll go through the two methods we have for experimental modal analysis, the two methods we use for extracting the modal parameters. And again, as Dieter said, please feel free to use the chat function if you have any questions. Then we will try to answer the questions afterwards. So, just to introduce modal analysis, let's go to the very simple case where we have some kind of structure that is vibrating for some reason. This is what we could say is a physical domain that we are looking at here. When we do modal analysis, we are trying to extract, you could say, the modes of vibration of this structure here in a more systematic manner than just looking at it here in the physical domain where everything is mixed together. So when we do modal analysis, we separate the different modes of vibration from one another. And the most visible part is the mode shape. So there is a geometrical deformation of the structure that relates to a particular dynamic mode. Besides that, there is also other parameters that describes the individual dynamic modes. These are the natural frequency, the damping ratio, and when it comes to this experimental modal analysis, there is something more we can do besides what we normally can do with operational modal analysis, because we can actually get the actual scaling of the modes, how they are scaled compared to each other and so on. But this is what we can do in modal analysis. That is, we go from some measurements that we take at different locations on the structure here, and then we extract mode shapes, natural frequencies, and damping ratios. And we can do that in different manners. In the software, we have operational modal analysis, and then we have experimental modal analysis also. One is where if you only have, you could say, response measurements available, then it's operational modal analysis. If you have input and output measurements available, then it's experimental modal analysis. And this is also what I'm trying to illustrate here with this simple slide here. We have some kind of structural system, This system here we have to assume something about in order to make things work. First of all, we have to assume it's a linear system. That means it doesn't really matter if we are, you say, exciting with a weak excitation force or a more powerful excitation source. We should be able to get the same parameters out no matter what excitation level we have. If this is not the case, then we are talking about a nonlinear structure, and this is not really suitable for modal analysis in general. Then we have to turn to other, you could say, software tools. So we assume linearity of the structure. We also assume that throughout the analysis that we are doing, or the testing we are doing, the structure remains time invariant. We cannot have the structure is changing its dynamic behavior over time while we are doing the testing. We have to assume that things are stable and you say invariant in this way here. So these are two normal, you say, assumptions that are always made for modal analysis, and they are typically quite easy, or at least acceptable to obtain. What we have to do then is we have to excite the structure in order to get the modal parameters. So we will have to in some way supply some kind of input, some excitation that we can measure. And at the same time we have to measure how this structure is responding to these input forces. So we have to put some devices, some accelerometer typical, or other sensors that can in some way measure the vibrations that are induced by the excitation forces. So we have to measure the response also, we say. And for experimental modal analysis, it's very, very important that all the excitation that is supplied during the test can be measured. Because if there is some kind of excitation acting on the structure that is not measured while we are doing the testing, then we will actually not get the proper results that we are expecting. So it's very important that you in some way isolate the structure so that whenever you excite it with some force, it's possible for you to measure everything that is exciting this structure here. So this is a very, very important step for experimental modal analysis. Schematically, you could say the way we normally do it is we have a structure. We will put some sensors that can measure the response in one or more points on the structure. We will excite the structure with some input that we can measure. Here you see what we call an impact hammer. This is a small hammer that has a force transducer out here in the tip that allows us to measure the force that we are actually hitting the structure with. And the accelerometer that is put here can measure then the accelerations that are this input is causing of vibration. So there can be one or more of each of these devices here, but in practice you normally have, you say, the impact hammer, and then you have one or more accelerometers acting when you are doing what we call an impact test. So you go out and you impact in one or more positions. When you do that, you record the force that was applied to the structure. This is normally just a sharp peak, so there is a sharp impulse and then nothing after that. So that's why you see this kind of peak here and then nothing else in this, this recorded time series of the force. At the same time we are measuring then the response in the accelerometers. And here we filter, you say, this, this impulse through the structure, and the structure will then vibrate for a time. And after some time, this vibration will die out. So we have a kind of a free decay here, a transient behavior of the structure. And we are then recording this. And you say, depending on how much damping you have in this structure here, you get a short or a long vibration here. If it's a lightly damped structure, this one will go on for a while, and if it's a heavily damped structure, it will die out very quickly, this response here. What we then will do with these two sets of data we have here is we will transform these to frequency domain. Here we obtain a spectrum of the response. It looks like this, where we have all the peaks, where we have the resonance frequencies of the structure here. And then we also have a spectrum of the force. And when we have something that is very sharp in time domain, it becomes very flat in frequency domain. So therefore an impact like this is very nice, because it actually in frequency domain show that we are actually exciting a broad band of frequencies. So all the modes in this band here are being excited very nicely and more or less with equal force. So this is a very nice way to have a spectrum looking for the input forces that we are using for experimental modal analysis. These two are divided with one another. There are different ways we can do that. It depends on what kind of estimator we are using. But what we get out of it is we get a function that is called the frequency response function. It's a transfer function between input and output of this system here. And what you see here is a very clean function that actually only contains information about the structure. Because we have measured all the input and all the inputs, all the input and all the outputs. And when we divide this with one another, we obtain something that is only related to the actual structure. And this is really nice. And this is what we are looking for, and we are using in ARTeMIS also. There are other methods that relies on going back to time domain and then fitting things there, but we stay in the frequency domain and use this frequency response function in order to extract the modes. So this is our basis, and I'm going to show later on how we are using different ways through files or impact testing in the software to obtain these frequency response functions. It is always, you could say, the aim, the first critical thing we have to do, that is to get these into the software so we can start doing a modal analysis. There are different ways, as I said, to do this type of analysis. Most commonly you have impact testing, where you are taking your impact hammer and you are impacting different locations. If you do that, then you will see that if you're looking at you say the matrix formulation of a frequency response function, it is actually not only a one value. There is a range of values in a matrix, because there are as many columns as we have inputs, and there are as many rows as we have outputs. So if you have, you could say, a single accelerometer, and you have this input here being impacted different locations, then you will get one row with many, you could say, column entries. But this will be the information you get for every frequency in your frequency response function. It can also be the opposite, because you can also have a single input acting in a single location. That could be a shaker like this. And then you can position, let's say, an accelerometer that you move around. In this case, you have a single input. That means you have a single column. But because you're moving around with your accelerometer, then you get several rows in this one here. So now you get, you say, the opposite, the transposed version of the first one. But still, it's enough information to extract the modes of the structure. In some cases, you will see that if you now, for example, here mount two accelerometers instead of one, then you will get two rows here. If you mount two shakers instead of one, you will get two columns here instead. So this way you can add more if needed, and especially if you have closely spaced modes or repeated modes. If you have something symmetric you're testing, then it's a good idea to add more than one, so we have more columns or more rows. This is the two ways we are doing it. The way that I'll demonstrate with the software is the impact testing here, but it does not mean that we cannot import data from a shaker test and analyze that. That can of course be done. Let's see here a little more into the software now. ARTeMIS Modal, that is a package that originally was designed for operational modal analysis. where you are importing files with measurements, and then you are analyzing it with different operational modal analysis tools. But what we have done over the, I don't know, last 5 or more years is that we now have added support for experimental modal analysis, and also support for that you can actually operate different data acquisition systems inside ARTeMIS. So in order to open up for all of this, we need to add some plugins, as we call it. That's just licenses that are added into the license file that allows you to, or it opens up for different things inside the software. There are 2, you could say, licenses that are needed in order to make it really work, with impact testing and everything. And that is the so-called EMA plugin that opens up for that you can now use software for experimental modal analysis. And then there is a data acquisition plugin, depending upon what type of hardware we're going to use with the software. This plugin is then necessary in order to make the impact testing module work. So if you want to import files only and do experimental modal analysis, you can stay with the EMA plugin. If you need to also use the software for impact testing, using, for example, National Instruments, you need also the data acquisition plugin license for National Instruments. So this is the way we have created the addition of using ARTeMIS for experimental modal analysis. Besides using the interior impact testing module, you can also, as we can see here, upload files. It can be the raw time series files where you have input and output measurements. You can also upload frequency response functions that are already processed by some external software. And then you can do the impact testing also. This is the options we have, and I like to show all of them a little bit, or introduce it in this webinar here. So in order to do that, I have this test object here, this structure here. And in fact, I have it here next to me, so I think I'll take my camera here and then try to see if I can put it in a place so we can see it. Let me just lower my table. So sooner or later, I think you will be able to see. If you can see my camera, I hope you can do that. Then here you can see then the structure here. So it's a structure that is about, 30 centimeters high. It's of aluminium. We have mounted 4 accelerometers on one side and 4 on the other side, in this case here. I'm going to use an impact hammer. I have it lying here. And there is also, of course, a data acquisition system where everything is linked to. And this is a National Instrument system that I'm going to use here. I have 8 accelerometers. These are TEDS accelerometers, so it's very convenient because then I don't need to type in all the calibration information. Then I have this hammer, and then I'm going to use what we call fixed output and rolling input in this case here. So I'm going to impact different locations on this structure here. So I'm going to use this one here both for an impact test, a very small one I'll do, but also show you how you can actually also import the data, either the raw data or the processed FRFs from a universal file format. So you can see how you can actually get things into the software. So this will be the first part of this webinar here, you could say. So we'll start here with the impact testing part of it. And when we do impact testing, we have actually 3, you could say, ways we can do it. We can do what we call fixed output and rolling input. We can also fix the input and then we can roll around with the output. And we can do the thing where we are moving both input and output. The one I'm going to use here is that I have already mounted my 8 accelerometers, and then I want to impact a couple of places, so I'm using a rolling input in this case here. What we need in order to make impact testing is we need to generate a geometry And then we need to also tell where on the structure that we are measuring it, and what is the input and what is the output. So this is the first part of it, that is to model all this. And then of course we need to link up to some data acquisition system, and currently we are supporting these 4 different suppliers here. And again, the one I'm going to use is the National Instruments modules. Let me try go to the software now. I have already, because I have in several other webinars that you can find on YouTube, our YouTube channel, I have shown how you can, create a geometry, you can assign the different channels and so on. All the things here, I've done that several times, so I thought this time here I'm going to start without doing that, because then I can talk about other things as well in 1 hour. So I have already prepared, you could say, a geometry, as you can see here. I have already added 8 output channels and 1 input channel in the first setup here. If I now click on this one here, you can perhaps see that this one over here lights up this hammer here, showing that this is the first impact or input location here. So that channel 9 you see here, that's actually this point here. Then we have the second setup. Again, we have placed the accelerometers in the same locations, but now it is this impact here, or this position here, that we are using for our input channel here. So we have these 2 setups here, and that should be sufficient in order to extract some nice modes of this structure here. The next we have to do is we have to go to the actual impact testing module. So I have to select now what hardware I have connected, and I have the National Instrument here. So what it does now is it goes out and it checks what is actually connected here. It finds all the TETS sensors and read the calibration information directly. So all the first ones here you can see have already been found, and it knows who the manufacturer is and calibration constants and all that. But the only thing we are missing is our impact hammer, because that one unfortunately does not have TETS information built in. But we have already added, you could say, the calibration values into an XML file that is lying on this computer here. And what I just have to do is I have to find it in that XML file. So I have to tell that it's in fact the force transducer I have here. And the one I'm going to use is this impact hammer here that I have defined already. So in this way I have to do a little bit of manual work in order to find this sensor that is not having TETS information. But it's not like you have to enter, you say, the calibration constants every time you use it. You only have to do that the first time where you are setting up this information in the XML file. And that XML file you can actually just copy to other computers if you need to do testing on other computers as well. Then they will be lying there and can be used also there. But now we have the 9 channels connected. And then we just wait, and then we get now into the impact testing module here. We have over here we can ultimately see different things. Time domain data, that means, for example, the impact and the response in time domain. Over here we will be able to see the processed information. That means, for example, the spectrum of these recordings. But in order to see a little bit more, we can enable a few more of these. I need to first link the sensors to the project channels. Now I should be able to add it. Yes, like this. So now I have 3 views here. I have the 2 acceleration, and then in the bottom here we have actually already enabled the force. So the bottom down here will be our force that we will be able to see in time and frequency domain. What we need to do is we have to configure the level of triggering of the hammer, and also configure if we need some kind of windowing on input and output. So in order to do that, we go to this we call hammer setup up here. So I click on this one here, and then now I get this other dialog here popping up here. And the first I'm in here is, you could say, the hammer trigger setup. What I have to do here is I have to select first of all what bandwidth I want to use, what should be our maximum our sampling frequency. I select 5120 Hertz. And then I need to also select a resolution. That means how long, how many samples do I want to record. And this is a lightly damped structure, so I would like to have a little bit more than 1024, so I will take the double here. And then this is something you can always change if needed, but let's start with this. Now I start it, and then I have to grab my hammer and then start impacting a few places on this structure here in order to get the trigger set up for when the recording should start. We can see here the different impacts showing up here now on this diagram here, and I can now stop here, and then it has now suggested this level here, and I can of course move it up and down if I'm not satisfied, but I think this is probably okay. So this will be the trigger level. So every time you have an impact that produces a force that exceeds this limit here, the recording will start. Then we go to the next step in this, that is to see how does it actually look when we now do a measurement. I normally like to see raw data and the window that I'm using. And in a case of, you could say, the force, at least I will always use a force window. The force window will allow the impact to pass, and then after that it will then remove anything else, you could say, that might be there of noise for the rest of the signal. There's no need to record all this noise here. At the same time, we can do something similar with the response. And now we can use, again, we can see the raw data and then the window. And there are different options here. We can, of course, use a rectangular window, as it's called. We say none here, but it just means that we are not applying any kind of window to the data. We can also try to use an exponential window. And then there's a value here that we have to set. And this value here is actually, you could say, what is the fraction that is left compared to the start when you are at the end of your data segment. And here it's set to 24% of the initial value, but we can try and reduce it to maybe 1% instead, like this. So now it will really damp out, you could say, any response that might be left. And this is necessary because we cannot have that the response is not completely died out at the end of the segment. Then we will have troubles when we start using the FFT to obtain our spectrum. So this is what we can try, and now let's start it and see how this looks then if I make an impact. Triggered. And here we can then see over here we have the force in the frequency domain. It's not completely flat, you could say, or constant, but it's very flat and very broad, as we can see, so that's nice. Here we have the spectrum of the response. Over here we see the actual impact, the input force. We see how the force spectrum operates. The same down here. We have the raw signal here, and now we also see how we actually have the exponential window decaying to more or less zero at this end here. It's down at 1% here compared to what it started out with, which was 1, of course. This looks good. Let's stop and then accept these settings we have made here, and now we are ready to start the actual impact testing. And as you can see here, we can zoom up a little bit here so we better can see what's going on. We can also make the arrows a little bit bigger here. So now at least I can see them here. So this is the first impact position I have to do. And I have to do 3 as I've set it up to here. So I will start now, and then I will impact 3 times at this location over here. And every time I have to look and check out that it's not too bad what I'm doing.
Triggered. Measurement complete. Preparing next setup.
And now it
Recording
switches
started.
automatically to the next setup. So now I have to go to the other location here and then do exactly the same.
Double hit.
Oops.
Triggered. 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 Measurement complete. Test is complete.
So that was it. It's not so much this time here. But this should be enough to extract the modes. So now we are finished. We have done all the. We can go and see the different results we got in the managed measurement part here. So if I go here to the first setup, I can select the impact number 1 here. And then I see the first one I produced. I can also here see in the frequency domain. If I want, I can also select other things. Instead of the spectrum, I can also select the FRF or coherence or whatever. That can be done also per channel, you can say in this way here. Down here you have a little diagram also. It actually is a visualization of the frequency response matrix. You can see we have 2 columns and then we have 8 rows in this case here. They are all green, and that indicates that we have actually processed, you could say, the full matrix here now. If I went here halfway through my test, I would have seen that this part over here would have been red instead of green, to indicate that I am missing this part of the frequency response matrix. But when everything is green, that's of course nice, because that means we are ready now to go to the actual modal analysis. And that is done by clicking to the next part here, the analysis part. And here you can actually see the first we will go to here is the prepare data. This one here is quite simple here because we have already processed the data. So what you see here now is the mode indicator function. And up here we can then see, of course, the geometry. But here we can then see this is the singular value decomposition of these frequency response matrices we have throughout the whole frequency range. We have done this singular value decomposition on it, and we are plotting then the singular values, and this gives us this very nice diagram where it's very easy for us to track all the modes and how they look. This is the impact testing module, you would say, very quickly gone through. But I think I will leave it with that, and then we will proceed with the next part here, which is how can we actually produce, you could say, or reach the same point if we are not having, you could say, the hardware, but we just have, you could say, the recording of the response and the input available. And to do that, we will have to use other parts of the software, and normally the part that I would use for this is the so-called configuration file. So you should imagine that you up front you have only measurement files with input and output measurements in time domain. And this, when we visualize it, it looks like this. In this case here, this is 3 impacts, as you can see, done and recorded after one after the other. And here we have then the corresponding impacts in the input, the force of it, showing up here. So this can be uploaded into the software through the configuration file. I can try to show you here. I have here of the same structure here. This is how this configuration file looks. It's a text file. You can define different things. There are keywords. Header is a keyword where you define the title. Capital T is your sampling interval. Here you put whatever sampling interval you have. Here you can define the geometry, the nodes. So the first column here you have, this is the node numbers. This is just an integer value. And then you have the x, y, and z coordinate here. And then you can also make trace lines between the different nodes that you have defined, and you put that in the lines section here. So here you tell that you want to have a line between 4 and 10, node 4 and node 10, and then it will draw a line like this. And the same you can do with surfaces that are making things look a little bit more solid. These are triangular geometry elements, and you just specify 3 nodes, and then you'll get a triangular surface drawn in between these. And then finally you have to specify the files where you have the actual recordings in of your input and output measurements. And we have a binary file here that consists of this for the first setup and another one here for the second setup. And then in this configuration file you have to actually specify for each of the channels where the channel is located on the geometry. So the first one is located in node number 8. You also have to specify what direction. So there is a directional vector here. These 3 numbers here, x, y, z, tells what direction this sensor is located in. Then there is a value here that we don't really have to care too much about. It's just the dB reference value that we use in order to make diagrams in frequency domain. When we want to show them in dB scale, we normally have to divide with some number, and that number can be you could say defined by standards, but normally we just put it to 1 because it has actually no meaning. It does not in any way affect the results that you get out. So just put 1 if you are not able to find better values. Then we have the unit these measurements are made in, and you also have the type of measurement specified here. And it's a little bit important that you place these information here. You will see down here it says Newton and then it says force. Because when you load this file here into ARTeMIS, this is the way when ARTeMIS is loading the file, it can actually then detect that because there is a force channel, then it's most likely that it's a classical modal or experimental modal analysis that you want to do. And then it will be asking you, is this what you want to do? If you say no to that, then it will disable the force channel and it will then make an operational modal analysis project out of it instead. So it's a little bit important that you specify, you say that it's a force channel. Otherwise, it's not so easy. And you do that for both these 2 measurements here that you have been making. And what you will see is that all the accelerometers, they are placed in exactly the same channels, nodes, and in the same directions in the 2 measurement files here, or for the 2 measurement files. And this is the way that ARTeMIS can then detect that all these accelerometers, they are you say, common points. So they are being colored blue inside when we upload it, because they are not moving around. The only thing that is moving around here is the force that is changing from one node to another one, as you can see. So let's try to load this one along with the 2 measurement files here. We go to ARTeMIS again, and we can just go out of this project here. And now I can find this file here. Let's see, I have it here, somewhere there. This is my configuration file we just had open, so I can just open it. And now you can see how because it already has read the information, it can now see that there are force channels available. So now it's asking, do we want to use it for experimental modal analysis, yes or no? And we say yes in this case here. And now we have our signal processing, you would say, dialog here where we can configure things. And here we can, for example, configure that we would like to use 2048 as our resolution. We don't want any overlap. We now have 3 averages that matches the 3 impacts we have. And then let's see, I think everything is good. Then we have opportunity now to put also the different windows here. And now we can actually start. And now we can process, as you can see, and we get exactly the same one more time. Okay, so this is how to do get the FRFs from configuration file format. And what else? Then we can do the last. And that is to go to universal file format and then actually load it in the similar manner. Here we, instead of using raw data, we now have processed data that is already produced by other data acquisition systems or modal analysis systems. They can always store things in universal file format, and then we can actually now import it into the software also. So this is the third option we have available, simply to load universal file format files. And if I do that, I have similar files lying here. I can just close this one here again. And let's see, then I can go to this. I have this universal file format option here that allows me to load, first of all, a file that contains the geometry. So that one has to be available also in this case here. So I load this one here. And then I can also load the FRFs. So they're lying here in another universal file. And then I can open it. And I'm now asked, is looking through, you could say it's looking through the file. And it's seeing that you have actually FRFs only in this file here, but it could actually be that you also have other things. It could be that you have, let's say, coherence, you have modes lying there, other things. So it's very important that if you have other things, that you only select the FRFs, because the other things doesn't really make sense to put into the analysis. But in this case here, as you can see, there are only FRFs available. So we'll just import all of these. And then we are back where we are before, but now we don't have to do anything because everything is processed outside the software. We just using the FRFs that in some way has been produced somewhere else. And we have the geometry, as you can see up here, also available. So this is the easiest way, you could say, to get started with the experimental modal analysis. So let's just stay here now and then produce some analysis results. Before that, let me just go here to this little slide here, just to say that we have different types of estimators, of course, in the software. We have something we call non-parametric frequency domain methods. And we have some in our operational modal analysis. They are called something with frequency domain decomposition. And then we have experimental modal analysis. There we have what we call complex mode indicator function. And it's because we are using the complex mode indicator function to do peak picking on. And this is the idea of this method here, that we simply are picking out the peaks we have here. And doing that, we can then obtain the information that we need in order to estimate mode shape, natural frequency, and damping ratio. And the way it works is that for each frequency here, when you have an FRF, you can then apply this singular value decomposition. So when I do now a peak picking on the peak here of the first singular value at some frequency, I'm picking out this singular value here. But along with that singular value, there is also something called a left singular vector. And it turns out that this singular vector here is a really nice estimate of the mode shape. So this is the way basically it works. This is the way we get the initial mode shape estimate that we need for further processing. There is one little thing to keep in mind here, but it's not something that you need to think about so much, but the software has to do it for you. Because we are always using the left singular vectors here. And that means when we supply or we use the singular value decomposition on a FRF matrix, then it's a little bit important what we have, you could say, in the row space of this matrix here. We can go here and see it. Remember that if you had impact testing, you had maybe only one row, and then you had many column values, because that was all the places you went around and you impacted. So we have one row, and then you have many columns. If you have a shaker, then you had one input, and then you had many row items where all your different accelerometers were located. So here you have a row, which is what we want to have. So if we are using, you could say, singular value decomposition to use it with this method here, and it's impact testing we have been doing where we only have one or two perhaps rows, but many columns, then we actually have to transpose this matrix first and then do the SVD. This is not something that you have to be concerned with. The software will do it, but this is how we make it work. And once we have done that, then it's just a matter of making the peak picking. We can try going here and doing that. So I go to estimation now. And the first thing you see here now is CMIF. I can now try to hit this button here, and then I can go here to the top, to the peak, and then I can double click. And as you can see here now, I will have a mode shape here animating over here. So this is what we have to do, no more, no less. You can also see you get a frequency and you get a damping. This is actually extracted from the red part here that you see here. The red part here is made in the same manner as we do for our operational modal analysis that works in frequency domain. So we are getting it from a MAC analysis where we are comparing the mode shape up here with any potential mode shapes all the way down here and all the way on the other side. And as long as they look the same, we are capturing all the singular values. And then we get the top part of this single degree of freedom model here. And this allows us then to actually get, you say, an improved estimate of the mode shape, because we now have many mode shape values we can average together. And it also gives us the opportunity to estimate the natural frequency and estimate the damping. And we do that in frequency domain with this method here with a simple least square estimation. But this is the way that the CMIF peak picking methods, as you can see, are working, and it's very simple to just pick your way through all the different modes here, and you get a very nice feeling about the data that you have been working with, and because it's very easy to operate like this. So this is the first of the two methods. The other one, let's just see if I have anything else. I already talked about this. The other one is a parametric method, we call it. It is in the same kind of way, working in the same way like our SSI methods are working for operational modal analysis. But for experimental modal analysis, it's called RFP-Z. The way it works is that we have to estimate a range of parametric models. We can then extract frequency, damping, and mode shape from these. And then we can construct a so-called stabilization diagram. So we can actually identify which of all these different results we have obtained here that are related to some structural modes, physical modes. And then from this diagram also, the software can search through it and then find all the modes that it can see repeats themselves in different models, and then it make an average of these to provide a list of global modes over here. So this is how it essentially is working. Behind there is some mathematics, of course, and what we have to do is we have to fit a rational polynomial like this, where we have a numerator polynomial here that is different from the different FRFs, and then there is a common denominator polynomial that will be the same no matter how many FRFs we have. This is defined for a single FRF and a single frequency in what we call set domain, that is a little general frequency domain. This has to be extended because we are not only having a single FRF and a single frequency here. We have multiple frequencies, of course, from 0 to the Nyquist frequency, and we have also been impacting different locations and measuring output in different locations, so we have a range of FRFs available also. This means that we have to put this a little bit together. For one FRF, you get this kind of formulation here. So now you have actually all the different frequencies represented from the FRF in this formulation. It's still a single FRF we are looking at. But in this way here, we can now, from a single FRF, we can actually estimate, you will say, the unknown coefficient of this rational polynomial. The rest inside these different other matrices and vectors are things that are known because it's from the FRF or frequency axis that things are coming, so it's something we know. So this is a way we can actually make a regression and then we can find this. But we don't only have a single FRF, we have many. So we have to complicate it even more. And we do that by stacking all these FRFs, all the formulations of the FRF on top of each other. And then we get this type of formulation here now, one for each of the FRFs, as we can see. And then with a lot of mathematical gymnastics, you end up with some formulation like you see down here, where you now have a regression problem where you have this R matrix here is known, this R vector here is known. The only thing unknown here is the coefficients of the denominator polynomial, and then of course you can find these by inverting this and multiplying over here. Once you have A, you can inject it into this one here, and then for each of the FRFs you can actually obtain then the vector of B coefficients. So this is a little bit complicated, but this is what is happening inside the RFP-Z method. Once we have, you could say, the A polynomial found, we can find the roots of it. The roots are actually equal to the eigenvalues of whatever problem we are looking for here, or the poles as they are called also. But they are coming from the, you could say, the roots of this denominator polynomial. And once we have these poles, we can put it into this formulation here where we have the FRF relation to the poles through the residues. And the only thing here is unknown is then the residues, and then putting everything together, we get another regression problem that allows us then to find the residues. And once we have those, then we can extract the mode shapes. So there are a lot of things, as you can see, going on here. But this is in essence what RFP-Z is about. Let's go and see how it looks inside the software. If I go here to RFP-Z and I select first setup here, then you can see I get a diagram here where I have a model order up here. This is then you could say the order of this denominator polynomial, how many coefficients we are going to put in there. And then we have the axis here, the frequency axis, this way here. So I can simply click this button here and then say I would like to estimate all the models between 1 and 50 in this case here. And it does it for me, and automatically it then also finds out that all the red dots we have here, this is actually modes of different polynomial orders that looks the same, and they are being averaged together. So there's a small a up here all the way. This is because the software tells that we have automatically extracted a mode based on all these red dots here. They have been averaged together, the frequencies, the damping ratios has been averaged together, and the mode shapes. So what you get over here is an average of what you see over there, and then you can of course start animating it and see the mode shape here. And of course you have the damping also and so on in the list here. So this is how you get modes out from RFP-Z. Very simple actually. The only thing that you have to work with here is basically what range would you like to estimate? Is it only this part here now you want to find the modes from, or is it the full, or what is it? You can do similar things. You can move from the left here and then out, and then there's now only this part here you will be looking for modes in. And then you also have to tell the maximum model order here. This is also, of course, an important one, because if you have many modes, you need a higher model order. So this is basically the two things that you need to operate. Then there is, of course, all kinds of mode indicators and other things that you can fine-tune, but normally it's not really necessary. It's only these two things that you need. This is RFP-Z, and we can then end up trying to compare the things. We can do that in the validation here. Validation is available if you have the standard or the pro version of the software. Then we have this task here. And here you can then try to superimpose two modes from two different estimators, for example, and try to animate them together. And then you can see here that the red one is the RFP-Z and the blue one is the CMIF, in this case here. So here you can then do a validation and see how things are looking when you compare them with one another. You can also import other projects and compare across projects and so on. That's also possible. But this is in essence what we can do with experimental modal analysis in the software. Let me just go back to the presentation here. And then see, we have a final remark here. Just to summarize a little bit, that it's quite open, our platform, because we can do impact testing inside the software, but we can actually also import files, both processed FRFs, but also raw measurements, and then process it inside here and extract the results. We can of course also export all the results and all the data out if you want to do it somewhere else also. So in this way we have a quite open platform, both for input and output. And as you can see, we also support already different hardware. This list will hopefully grow longer as time goes, but this is what we support right now. And we have for experimental modal analysis, we have the two methods that I've just explained in this webinar here. And if you have standard or pro, you also have the validation that I showed in the end here to work with. All right, so finally, just some information about, you can find this presentation will be available probably also on our YouTube channel, and otherwise there will be other ones already lying there. You can find it here, and you can also search for ARTeMIS Modal in YouTube, then you will find it. There is our website, we have literature, and we have of course software to trial versions to download and test. Next user training course we are giving is next year in April here in Aalborg in Denmark. And of course you are all very welcome if you would like to join. They will be on operational modal analysis, experimental modal analysis and SHM modules. And the next webinar I'm going to give will be on operational modal analysis. That will be on March 6th next year. So thank you very much.